This is the discussion section, Math 6A, and today is the recording for week 3. In this video, we will talk about the derivative of functions. Let's think about the function f, which is defined on reason u, and our codomain is r to the n. So if our open set U is a subset of Rm, then x can be represented to the m coordinates. So we can say that x vector is represented by x1 to xm, right? Also, so let me think about the case that in R2, then there is the two directions, x direction and y direction, right? So we can differentiate the function f with respect to x direction and y direction. So there are two ways to differentiate the function. So if we think about the case I equal to 1, it means that f is differentiated by first variable. So in the case, it is fx. And also it can be denoted by f1 because we differentiate the function f with respect to the first derivative, first direction. Also sometimes it'll be written as d1f. It is also it means that differentiate the function f with respect to the first variable. It is all the same notation. So let me see, this notation means that we want to differentiate f with respect to xi direction at x. So it is the same as this limit. It means that we want to find the different f x plus ei direction minus fx, and we want to find this limit. Okay. Also, we can say that it is equal to d dt, while t is equal to 0 when we think about the function f at x with the direction ei direction. Here ei means the i's component is 1 and the others are 0. So x plus t ei it is the same formula for the partial derivative with respect to xi direction. Also, there is another concept, gradient. Gradient f at x means that it is a vector field. So there are m variables. How can we compute it is each component is the partial derivative with respect to the ith direction. So it is x1 direction, x2 direction, and xm direction. I think it is better to think about it by solving problems. Let's go to the problem. So here, we want to find fx to 1, right? So we want to use this definition by calculating the limit. Let's go. So to compute fx 2, 1, we just put the definition of the partial derivative. Since we think about the x direction, we use e1 vector. In this case, e1 is just the 1, 0. Okay. So I put x here 2 comma 1, which is the given point, and e1 is 1 comma 0, and here x is 2 comma 1, right? So I want to compute these things here. So first of all, it is 2 plus h comma 1. Since we know f of x comma y here, it is given, so we can compute the denominator, right? So I just put x equal to 2 plus h and y equal to 1. Then x equal to 2 plus h, so 2 plus h cubed plus 2 plus h squared minus 2, right? And if we put x equal to 2 and y equal to 1 here, then we get 8 plus 4 minus 2. Okay, so let's compute it. Then we get 8 plus here 3 times 2 square h plus 3 times 2h squared plus h cubed. So it is 12h and it is 6h squared plus h cubed. And also if we simplify this one, then 4 plus 4h plus h squared. So this minus 2 is just minus 2. And here we get 10, so it is minus 10. So there is only one term with degree 3, h cubed. And there is two terms, 6h squared and plus h squared. So there are 7h squared. And there are 12h and 4h. So here is a 16h. And you can see that there is plus 8 plus 4 negative 12, so it'll be deleted. So yes, this one can be presented like this, right? So we can say that if h equals to 0, then it'll be 0, so this limit must be 16. So we can say that our partial derivative with respect to x at the point 2 comma 1 is 16. Okay, great. However, there are more simpler ways to compute these ones. That is, this partial derivative means we think y as a constant. So when you think about the partial derivative of this function with respect to x, we think that this function have one variable x and y is just a constant. So we can differentiate this function like the derivative of a one variable function. So in this case, x3 x cubed is differentiate like this 3x squared, right? And here, when it differentiate this term, x squared y cubed, then y cubed is a constant in this case, right? So I just put y cubed here, and I differentiate x squared. Then it'll be 2x, right? So I got this one. And this one, the last term is just a constant. So if we differentiate the constant, we get 0, right? So it is our partial derivative. And we want to find the partial derivative at 2 comma 1, right? So I just put x equal to 2, y equal to 1 here. Then we get 3 times 4, so 12. And here, 2 times 2 times 1, so it'll be 4. So we get 16, right? You can see that we have the same answer, okay? So this method would be better than the uh, other method, right? Okay, let's go to the another example here. Then you can calculate it quickly, right? Using the second method, we can say that if we differentiate f with respect to x direction, then we just think about the think about the derivative of this function with respect to x, and we think about y as a constant. So we first differentiate these functions sine, so we get cosine here, and we wanna differentiate this function with respect to x, and we multiply by it, right? And when you think about the df dy, in this case, we think x is a constant because we want to differentiate the function with respect to y. So our variable is just the y. So here first I differentiate this function sine, so we get cosine function, and we need to multiply the differentiation about the inner function here. So we get uh, what you want to do is d dy. It is better to use the partial notation here. Partial y about x over 1 plus y. We need to multiply this one, right? It is this. You can calculate it like this. Because 1 over 1 plus y is differentiated like minus 1 over 1 plus y squared. Okay, so you can get this one. If you are not familiar with this calculation, then just think about the case as usual. Your function like cosine 2x, if there is a function cosine 2x, you can differentiate it like the first we differentiate cosine functions, so we get minus sine 2x, and then we multiply by the inner function. I mean the differentiation of inner function. So we multiply by 2, right? 2 is the differentiation of 2x with respect to x. I use the same method here. So I first calculate the differentiation of sine, and then I multiply by the differentiation of the inner function. Okay. So you can calculate it like this. And let me see here. Now we want to calculate the directional derivative. It means that when you think about the R2 case, we differentiate the function with respect to x direction and y direction. However, there are another directions like this direction or this direction. There are many directions. So we want to differentiate the function in any direction. Okay, so let's go. The one thing that we want to focus on is v is unit vector. If vector has any length, then it'll be then this value a bit changed. So it is not a great condition. So we think about only the unit vector. So if the direction is given by the any vector like 1.2, then we need to find the unit vector. Here unit means the length is 1. So what you need to do is divided by the length of the vector. Okay. Then this vector represents the same direction and the length is 1. So in this case, it is 1 comma 2 over, when you think about the lengths here, it'll be root 1 square plus 4 square, so it'll be 5. So it is the unit vector, okay? We need to find the unit vector when the direction is given. Okay, in the case we want to differentiate the function here with respect to v direction, okay, then it can be calculated like this, and also we can say that it is calculated like this. After we learned chain rule, we learned that it is also same as this formula. It is gradient f dot product v vector, okay? Let's go to the problem. Here, I think problem 3, right? Okay, problem 3. Okay. Here we want to find the directional derivative of the function in the given point in the direction on the vector v. Okay, there are 2 examples and I want to focus on the second example. Here f is given by like this, and 1 to 3 is a point and v is the direction. Then the first thing what we need to do is find the unit vector u. So in the case, you can see that the length of v is given by root 2 square is 4 plus negative 1 square is 1 and 2 square is 4. So it'll be root 9, so it is same as 3. So by dividing by number 3, v divided by 3, we get u. So 2 over 3 minus 1 over 3, 2 over 3, right? It is the unit vector and it has the same direction with the vector v. Okay, so we want to find the directional derivative duf. It is same as d dt fx plus tu. It is the definition of the directional derivative. Okay. Okay. So we can say that since our x point is given by 1 to 3 and u, our unit vector is given by like this, we can say that we want to find this value, right? 1 plus 2 over 3t, 2 minus 1 over 3t, 3 plus 2 over 3t. Okay, cool. So I put this point in the f x comma y, okay? I think I forgot to add here x comma y comma z because there are 3 variables. X comma y comma z is right. Sorry about it. When I post this PDF file on Google Drive, I will write x comma y comma z here. So if we put x equal to 1 plus 2t over 3, then it is squared here. And we want to multiply by y, so it is y and plus y squared times z, right? Okay, cool. So let's calculate it. Then you can simplify first and take a derivative with respect to t, but I just take a differentiation first. So let me see. What I did is I did a product rule. I mean, I differentiate the first term first. So I get 1 plus 2t over 3. And we need to differentiate the inner functions. Then we get 2 over 3. So I multiply by 2/3, and then I multiply the next term here. Plus, in that case, in this time, we put the first term like this, and we need to differentiate this term, then we get -1/3, okay? And then here, also I calculated it using product rule. So I first differentiate this term. So it'll be 2 times 2 minus t/3. And we need to multiply the differentiation of the inner function. Then we get -1/3. Okay. And then we just put the last term here. And this time we want to find this thing, we put this thing here, and we want to multiply by the differentiation of this function, then we get 2/3. Okay, so I differentiate the function with respect to t here, and what you want to do is we want to put t equal to 0. If we put t equal to 0, then we get this one must be deleted, this one must be deleted, and this one must be deleted, and this one must be deleted, and this one must be deleted. This one also must be deleted. Then we get 2 times 2/3 times 2. So it'll be 8/3, okay? And the second term is -1/3, just the -1/3. And here, 2 times -1/3 times 2 times 3. So here, 3 is divided by itself. And so we get -2 here. And the last term, 2/3 times 2. So we get, just a minute, here, 2 squared. Okay, 2 squared. So 2/3 times 4. So we get 8/3. So let me see. It'll be, if we calculate it, then it is 8 plus 8 is 16 and -1. So we get 15. It is the same as 5. And so 5 minus 4 is equal to 1. Okay. So we get the value 1. And you can see that it is a very tedious computation. So there is another way to calculate it. Let me see. Let's go to the things here. Yes. As I said before, there is another formula like this one. So in the case, if we find the gradient vector and the direction, then we just do dot product, inner product here. Okay. So first thing is also find the direction vector here. It is the unit vector. So we know that it is just the 1/3 of the given vector v, right? So it is 2 comma minus 1 comma 2. And then we want to find the DOF. So in that case, we want to find the gradient f, and we will inner product. We will do inner product with respect to u. Okay, so we want to find the gradient f. To find the gradient f, we want to calculate f1, f2, f3. It is the partial derivative with respect to each direction, x1 direction, x2 direction, x3 direction. In this case, x direction, y direction, z direction. So if we take a partial derivative with respect to x, then it is just a 0 because it does not have x terms. So in the case, we think y as a constant because we differentiate the function with respect to a variable x. So we get 2xy, okay? So here, if we want to find the partial derivative with respect to y, then here is y, and x and z are constant. So here x squared is constant, so it is the first order term with respect to y, so we get x squared. And if we differentiate this function with respect to y, then we get 2yz, right? And the next thing is the differentiation with respect to z direction. So the first term must be constant because there is no z term. And the second term must be differentiated like y squared, okay? So we can calculate gradient f quickly here. And our x vector is given by 1 to 3, right? So we want to put x equal to 1, y equal to 2, and z equal to 3 in the gradient vector. Then we get 2 times 1 times 2, so we get 4. And the second coordinate is 1 plus 2 times 2 times 3. So it is 13. And if we multiply by here, y is 2, so 2 squared is 4, okay? And we are in a product with the vector u, okay? Then inner product is calculated like the term by term. So 4 times 2 over 3. Actually, there are all 1 over 3 terms I just put here. And let's say that 4 times 2 is 8, and 13 times minus 1. Negative 1 is negative 13, and 4 times 2 is 8. So in this case here, it is 3, right? 16 minus 13 is 3. Okay, so 3 over 3 is 1. So we get the directional derivative. The value is 1. Okay, you can see that this one is the same solution with this method. Okay, since we can calculate the gradient vector quickly, this method is easier. Okay, let's see. In this problem, we want to find the maximum rate of change of f at the given point, at these given points, and the direction in which occurs. Okay, it means that we want to find the maximum rate of change of f. It means uh, our rate of change of f is the directional derivative with respect to f. Sorry, it is the directional derivative of f with respect to v direction, okay, at our given point 4, 1. And we want to find the maximum. It means that our maximum value. So if we put absolute value here, we can see that it is the same as, directional derivative is calculated by the gradient vector and the inner product with the direction vector here, right? And we know that this formula can be calculated like gradient f 4, 1, 4, 1, and v and cosine theta, right? We know this equation. Sorry, it is hard to write down using mouse pad. Yeah. Actually, v is a unit vector, so it'll be 1 all case, right? And our gradient f at 4, 1 is just a constant vector, so it is the fixed number. So you can see that this value, it has the maximum at theta equal to 0, right? I mean, this term has the maximum when cosine zeta has the maximum in that is zeta equal to 0, and it has the minimum zeta equal to -0. Okay, so let's think about it. Maximum rate of change of f. Okay, so since we know that this directional derivative is calculated like this, we want to find the gradient vector first. So it means that we want to find fx and fy. Okay. Find the maximum rate of change. Find the maximum rate of change. Maximum rate of change. I think we don't need to take absolute value here. So just a minute. I think it'll be better to I mean here we can it'll be better to just think about directional derivative itself. We do not need to use an absolute value. Okay. Yeah. Okay. Great. Then let me see. Here, gradient vector, yes, we want to find fx and fy. So to find f with respect to x, partial differentiation, then y is just a constant. And if we differentiate root x with respect to x, we get 2 root x 1. Okay, so it is divided by 2, so we get 2y over root x. Okay, and here, yes, when we differentiate the function with respect to y, then we get 4 root x. Okay, and our given point is 4,1. So if we put x equal to 4 and y equal to 1 here, then we get 2 over 2, yes, 2 over 2, and we get 4 times 2, so it is 1,8, right? And we know that, yes, we know that this computation inner product is given by like this formula. And we know that v direction is just the unit vector, so it is 1. So it'll be 65 root 65 times cosine theta. Okay. And you know that cosine have the maximum when zeta equal to 0. So it has the maximum root 65 when cosine zeta equal to 1, right? If zeta equal to 0, then cosine zeta equal to 1, so we get the maximum square root of 65. And we want to find the direction v. You know that zeta is the direction of gradient f between the gradient f 4,1 and the vector v, right? And vector v. Then we say that this vector is, this angle is given by zeta when we use this formula. Then we know that the maximum attained when zeta equal to 0, it means that this direction v is parallel to gradient f direction. Actually, it is same as the gradient f direction, okay? So it is same as the direction gradient f gradient f here. So we know that gradient f is given by 1,8, 1,8. So v is the direction of 1,8. If we want to find the exact unit vector here, then it'll be root 65 here, 1,8, because we want to find the unit vector. However, if we want to find just the direction, then we can say 1,8, because we don't need to find the unit vector. If we want to just the direction, then we can say any vector, 1, 8 or 2, 16, like that. The length is doesn't matter. The length doesn't matter. Okay. So, okay, we solved this problem. And let's think about the another problem. Okay, and problem 5, we want to find all points at which the direction of fastest change of the function. It means that we also find the maximum of this and direction is 1,1 direction. Okay. It means that phase change means that our directional derivative will have the maximum. So it means that as we see in the previous example, gradient f and v has the same direction. Actually, not parallel, it is same direction, just the same direction. Actually, we can say that it is parallel because I mean, if there is a gradient f vector, and this is the v direction, then theta equals to 0. So we get the maximum of the directional derivative. But if we think about the fastest change, it means that we can think about the negative direction here. If v is like this, then theta equal to pi, and our cosine theta equal to minus pi, right? Then you think that it is the negative number, but you know, we want to find the fastest change. So we want to think the, I mean, plus 15 mile per hour is moving this direction, but minus 15 mile per hour is the negative direction. But they have the same speed, 15, right? 50. So when you think about the fastest trains, we can think minus direction, plus direction at the same time. So it means that gradient f is parallel to v if we think fastest change. Okay, so since our gradient f vector is given by fx and fy, and we can calculate it quickly because if we differentiate this function with respect to x, then we get 2x and it is constant. It is constant. So we get minus 2. So 2x minus 2. And if we differentiate with respect to y here, then 2y minus 4. We get 2y minus 4. And it is must be parallel to 1,1. Okay. So it means that 2x minus 2 comma 2y minus 4 is equal to k times 1,1 for some k, for any k here. So if we, since it is k in and the second term also k, okay, so we have the equation that first term 2x minus 2 is equal to the second term 2y minus 4. So if we divide it by 2, then we get x minus 1 equal to y minus 2. So we can say that our points are the line y equal to x plus 1. So this fastest change, if the direction of fastest change of the function is I plus j, then we can say that the points is or points on the line here, y equal to x plus 1. Okay. This is the similar problem, so you can solve these problems maybe. So I just put my calculation here, so you can compare the solution. Okay. Let's go to the differential of a function. When a vector valued function is given, then we can find df here. Since f is a vector valued function, so we get f1 to fn, okay? And also we have variables, m variables, so we can differentiate each function m. Yes, we can differentiate this function with respect to m variables. So for f1, we can differentiate with respect to x1 direction, x2 direction, like that, xm direction. And like this, we can differentiate fn with respect to x1 direction, like that, xm direction. Okay, so we get this matrix. It is the n by m matrix. N by m matrix. Okay. Let's calculate it in the example. Let me see here. We want to find the f differential of f when f is given by like this. Okay. Let's do it. So since it is our definition, we want to think about it. This one is f1. And this one is f2. And this one is f3. Okay. So we want to differentiate the first function with respect to x, then we get 2x. And we want to differentiate the first function with respect to y, then we get 2y. Okay. Then let's think about the second function here. Second function is second row here. We want to differentiate the second function with respect to x, then we get minus 2 minus 4y. So it is this element. And if we differentiate that function with respect to y, then we get minus 4x. Okay. And lastly, if we differentiate the third function with respect to x, then we get minus 2x. And here we get cosine y. Okay. So we can calculate the differential of a function f like this. Okay. Let's go. This is the last concept. Tangent plane of a graph. I mean, if there is a graph like where z equal to f of x is a graph like a surface, we want to find a tangent plane. I mean, if there would be x, y, z coordinates and there is a surface, then we want to find a tangent plane at some point. Okay. And the formula is given by like this. Here, if we find the tangent plane at this point, a comma b comma f of a comma b, then we can calculate it by finding the partial derivative here and put a, b, and f of a comma b here. Okay. Let's go find the problem 8. Yes. Find an equation of the tangent plane to the solid face here at the points 0, 1, 3. Okay. So for the convenience, we just put this f of x comma y. Okay. Then we can check that this given point 0, 1, 3, if we put x equal to 0 and y equal to 1 here, then we get 3, right? It means that 0, 1, 3 is the point on our surface, here. So we can think about the tangent plane at that point. I first find the partial derivative because we want to find df dx and df dy to find the tangent plane. So df dx is the partial derivative with respect to x. So since our f is given by like this, if we differentiate this function with respect to x, then we get minus 10x, right? And we know that fy is 6y. So our point is 0, 1. So our partial derivative is, if we put x equal to 0, then it is just a 0. And fy here, if we put y equal to 1, then we get 6. So at the formula here, we know that df dx a comma b is just a 0, so it'll be 0. And df dy here, we calculated it is 6. So we can say that 6 times y minus b here, b is 1, because we think about the point is 0, 1. Okay. And here we want to plus add f of a comma b. F of a comma b is f of 0, 1, and it'll be 3, right? We calculated f 0, 1 is 3. So our tangent plane at 0, 1, 3 is given by like this equation. Okay. Maybe in your homework 2, there are 2 or 3 problems regarding this tangent plane. So you can solve the problem like this method by using this formula. Okay. Since my Apple Pencil doesn't work well today, so I used just a mouse pad, so it'll be hard to understand some my drawing here. I'm sorry for that. I'm really sorry for that, and I will fix my Apple Pencil, and when I record the next week's discussion section, I will use iPad again. Okay. If you have any question, or it'll be if you think it is hard to solve problems in homework, then please drop by office hours or math lab. TA will help you. Okay. Yes. I will end the recording.